So in this week 3 set of lectures, we're going to finish off talking about the Euler method, look at a possible way of improving the Euler method, and then we are going to just do calculate some Maclaurin series. Okay, so this is a kind of a theory question that you could get in an assessment. Consider initial value problem. So the derivative is given in terms of x and y. And we've got the initial value of y at x0 is y0. So what two things do we know about the graph from the initial value problem? There's two things we know. First, we have a point, and from this we have the slope. So let's write down an answer. So from the graph, we know that x0, y0 on graph, and the slope there, now I'm going to write m for the slope at x0. So this big F of xy gives you the slope at any point. So we're interested in x0, y0. So if we plug in x0, y0, we know that. So the differential equation gives us two pieces of information. Okay, so Euler's method used the tangent of the curve at x equal to x0 to approximate the y value at a point distance h across. So use this formula to find the equation of the tangent at x equal to x0. So we have a point and a slope. Basically, we're using the information from the previous question. So we have y minus y1. The y1 here is the y coordinate we know as y0. Equal to the m is big F of x0, y0 times x minus, and the point we know in terms of x is x0. So all I just have to do here really is add on the y0 to both sides. So the equation of the tangent line is y equal to y0 plus, and I could write the big F of x times that term the other way around. There does not relate. Big F of x0, y0 times x minus x0. Okay, that's all that is. Find the value of y on the tangent at x1 equal to x0 plus h in terms of these. So what we're going to do now is, so we'll draw a picture at this point, just to kind of, if you're a little lost to help. So we have x-axis, y-axis, and we have some kind of a curve, something like that. We have a particular point that we know about. I'm going to draw it there. That's x0, y0. We draw the tangent at that point. Okay. And we've got the equation of the tangent line here. And now we want to know what's happening at x1 according to the tangent line. So all we have to do is plug in x1 into this essentially. Now x1, it says in the question as well, is equal to x0 plus h. So I'm not going to actually substitute in x1, I'm going to substitute in x0 plus h. So we're going to just substitute in x0 plus h into this equation of the tangent line. So get y is equal to y0 plus big F of x0, y0, the slope at x0. And now for x, I'm going to put in x1, which is x0 plus h. So I put in, instead of x, x0 plus h. And what's the story now? Well, x0 minus x0 is equal to 0. So we get the big F of x0 times h. And I'm going to write this in the form that is slightly more familiar to us. So in terms of the tangent, y is equal to the previous y value plus this term in the second bracket is just h times the slope, times step size times the previous slope. That's all that is. Okay. Next question, draw the tangent at this point. That's done in the picture in blue here. x1, this is here, as well as y1, this is here. Also show the error, so actually it's all done here. So that's not a great, I don't know, is that what I was supposed to have? So you need to understand that, okay, let's annotate this thing. You got the initial point you know about, which is x0, y0. You have the slope from the differential equation. The slope of the tangent at that point is big F of x 0, y0. You can travel along that tangent to get to the point x1, y1, and that is supposed to approximate the true value of y at that point, which is y of x1. And the difference between them, this vertical difference, is the difference between what you're actually looking for, which is y of x1, and your approximation. So that's all that's going on there. What do we got here? Using the above graph. Now, where is the above graph? Did we answer this question? Draw the tangent here as well as this. So presumably it's, so I'm not sure what's supposed to go in there, but maybe you needed your own above graph. Use the fact that dy dx, which is the slope, is the rise over the run, to derive this in it. So this is the formula we just had to do it in a different way. So if we do this, we should get it. So what I'm saying is that, so y1 is equal to, so this bit is y0 plus, I'm just going to call this up arrow. So this here is, so the length of this is y0 because the coordinate here is x1, y1. That should be okay. And so if you want to find y1, which is the y coordinate of this point B, you should be made up of y0, that vertical distance, plus the distance given by the arrow. So that's what I'm clumsily trying to say here. So I'm trying to say that y1 equal to y0 plus the extra bit in the arrow. And now what I'm saying is the slope of the tangent line is equal to, the slope of the line blue is given by the differential equation. Let's call it m equal to big F x0, y0. It's also given by the rise over the run. So what's the rise over the run here? Well, m is also equal to the rise, which is this big arrow here, over h. And so what we can find is that the arrow bit, if we multiply both sides by h here, that extra arrow bit, funny notation, is equal to the step size times the slope. But of course, the slope is equal to this big f of x0, y0. There's probably other ways of writing this. This is kind of nasty, to be honest. So therefore, using this thing here, the y value, y1, is equal to y0 plus the up arrow is step size times previous slope. So this is just kind of testing really to understand Euler's method, where again this next y value is the previous y value plus the step size times the previous slope. Okay, what have we got? This is the important bit. Show with the aid of a diagram how a large second derivative. Now, there's something we showed in the last week, that the local errors, when you use Euler's method, so that's how much extra error you get over one step. Now we showed actually that it was kind of less than or equal to the maximum second derivative. Now there was a kind of more complicated thing actually, but the maximum second derivative times h squared over 2. That was kind of an intermediate complexity statement, but the real things we're looking for is that, maybe we should have absolute values here. So we two statements that come, one that we focused on that says the local error in Euler's method is equal to order h squared. That was the big one we were focusing on. So it meant when, and we'll see it in a moment, when say you half the step size, you quarter the local error. And that just says that the local error is less than a multiple of h squared. The multiple here is the second derivative essentially divided by 2. But it's also less than a multiple of the second derivative. So it's also so this is just kind of revision. The local error is of order second derivative. Now I can put in a max. And what that means is, so here, so the local error is order h squared. If the h gets bigger, then the errors get bigger. Like if you double h squared it gets 4 times as big. So doubling the step size increases the error by a factor of 4. Now this statement over here says, as say the second derivative doubles, the error doubles. So that means that a big second derivative is a problem. And so this is to show with the aid of a diagram how this actually causes an issue. Right. Now if we zoom in on this point, we have some kind of a slope. So here the slope is equal to, say, f of x0, y0. And then we assume, as we approximate the red curve, we're assuming a constant slope over a step size. Assuming, oh, can't spell this. Gosh. Assuming constant slope, because that's how Euler's method does, constant slope, say between x0 and x1. That's what going by the tangent is. But of course, if you actually look at the curve, slope is changing. So this is kind of explaining what's going on here. So you're going to get errors if the slope changes a lot. If the slope changes, it doesn't change, it only changes a little bit. The constant slope approximation is going to be pretty good. But when the slope changes a lot, so here, like say, I mean, you could put a number on that. So the slope there, look, it gets steeper. It's steeper here. So the slope is increased. And if the second derivative changes a lot, if the slope changes a lot, you're in trouble. Okay. So when the slope changes, as per the diagram, Euler's method runs into trouble. The slope at each point is given by dy dx. Okay, so if dy dx changes between x0 and x1, or between xi and xi plus 1, Euler's method is going to have errors. And the bigger that change in slope, the bigger the error. If the slope changes a lot, then the rate of change of slope is large. So we have problems when the rate of change of slope, which is the same as the rate of change of the first derivative, is big. And the question now is, how do you get the rate of change of dy dx? And of course, the rate of change of a function is the derivative. So you have problems when the derivative of the derivative, the rate of change of the first derivative, which is the second derivative, is large. So when you see a curve that has the slope changing, that means it has a second derivative. So something where the slope doesn't change at all, second derivative is 0. That's a line. Yeah. Okay. So that's that. So that's that argument. Yeah. Another question here. So this is kind of an analysis thing. Consider initial value problem. Using Euler's method with a step size of h, it can be shown that an upper bound for the local error is this. So this is an upper bound for the local error. So really that's to say that the absolute value of the local error is less than or equal to the second derivative max. That could be on any region over 2. Okay. So, oh yeah, so no, it's the maximum between x0 and x1. What does it mean to say that the local error is order h squared? So it just means that it's less than or equal to a multiple of h squared. You'll get away if you just say it's a multiple of h squared, but we'll say it's for some k the local error. Now maybe we'll assume, like I keep putting absolute values around them, maybe we assume this is positive or not. I won't be too fussy on that. So the error, the absolute value of the local error is less than or equal to a multiple of h squared. You can write that in English as well. So what does it mean to say that the local error is order h squared? It's less than a multiple of h squared. That's all. Okay. And this is, look at the formula up here. Sure enough, it's less than a multiple of h squared, the k here being the maximum of the second derivative over little subinterval over 2. Show that if we use Euler's method to approximate this, that the global error is order h. So this was something in the notes. Now, considering that the assessment is open book, there might be a question about whether I can actually ask you this thing or not, but it's good to understand it. I might even give you the argument or something like that and ask you to ask something about it for argument's sake. Okay, so the total range here is we're going from x0 to x0 plus nh. So we're going from x0 to x0 plus nh. So I'm going to call this distance L. I possibly caused it T previously. Well, maybe there's a bit of confusion there between L for local and T. Okay, so let's call it T. So the total range of values that we're looking at is T, and that's equal to N times H. So in other words, there's N step sizes. I'm not sure exactly what we're going to do with this. Okay, so let's see. So the number of steps N, we might have to see what comes up. You know what, I'm going to leave this bit at the bottom and we'll get to it. Okay. So the local errors are all multiples or less than or multiples of h squared. Therefore, the global error is n local errors. Now I'm going to do stuff with the absolute values that you can probably strictly leave out here, but let's see. So the absolute value of the global error is equal to the sum of all the local errors. The first local error plus dot, 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 up to the last local error. Now there's something called the triangle inequality, which basically says that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. So I can use that here to say that this is less than or equal to the absolute value of the first local error plus the second local error plus the nth local error, etc. Okay. We also know that all the local errors are less than a multiple of h squared. Now we can take these constants to be different. So k1 times h squared is the first local error is less than that, plus dot, 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 plus kn times h squared. Now these constants k here are all positive. So we want to take a worst case scenario. We're going to take the maximum of them. So let k star be the maximum. So we want to find, so we got all these n local errors. We're going to take the worst case scenario. We're going to take the biggest of them. So we do that by taking the max for all these constants ki. So then this thing is less than, just put this in its own box. So this thing here is less than or equal to k star n squared. Sorry, where am I going with n squared? H squared. That's the first one. First local error is less than the biggest local error. Dot, dot, dot. All of them are less than the biggest local error. And how many terms here? Well, there's 1 to n. There's n of them. So this is equal to n times k star h squared. And now what I want to do is I want to have this in terms of h. See, there's a relationship between n and h. So what was happening earlier on becomes relevant. So I won't go on to back to the previous page. I'll just say, okay, so we had that n step sizes gave us the total range, which is the length of the interval that we're studying, which is in our control. And so if I divide both sides by h here, I get that n, so I don't want the n in there, to be t divided by h, because I want it to be order h no matter how many step sizes I have. So I want to get rid of the n here. So this then becomes equal to, so the n is t, which is the width of the interval. So you might be interested in what's going on between 0 and 60. So the width of the interval will be 60 divided by the step size times the k star times the h squared, and you've h squared divided by h, which is h. So you have t, which is some fixed constant, the width of interval you're looking at, k star, which is some constant, times h squared divided by h is h. And that is equal to order h. So we've got altogether then the global error. Now we've used 1, 2, 3 inequalities, but ultimately the global error is less than a multiple of h. This would be the constant there. And therefore the global error is order h. So that means that if you want to half this, the global error, which is the error at the very end, basically the error overall, like, so you look at the error like in the first step, but you could have 100 steps and you want to find maybe the error at the very end, something like that. It's going to be less than this. And if you want to make that error smaller, say decrease it by a factor of 10, this shows that you're going to need to decrease the step size by a factor of 10. But that has a problem because t is fixed. If you make h smaller, the number of steps has to get bigger. And that's kind of the catch with Euler's method. To make it more accurate, you need more and more and more steps, which may become a bit difficult for a computer eventually. Okay. So next thing, what's the effect on the local error if we quarter the step size? Now I'll write down our little statement about the local errors. So we know that all the local errors are order h squared. That means they're less than or equal to a multiple of h squared. Now at this point, we'll assume that they are equal to a multiple of h squared. Okay, so if you just say, oh, quarter, it'll reduce by a factor of quarter squared, that's fine. Or multiply by quarter, it'll be, the local error will be a multiple of a quarter squared, multiple of 1/16. That's fine if you understand that naturally. If you don't, here we go. So here's the explanation. I would take the answer. Let's hear the explanation. Let epsilon 0 be the local error with a step size of h. Let epsilon 1 be the local error with a step size of h over 4. So we know that the local error is a multiple of h squared. So epsilon 0. Now we're being a little bit dangerous here because if you change, say, the step size from h to h over 4, you're going to be changing the constant. But we'll just kind of won't worry too much about that and say, oh, we're always using the worst constant over the full interval. So we won't be too fussy, basically. We're just trying to get some rough understanding of what's going on here. So let's go with constant times h squared. So that's the local error initially. So now we're changing. So what I'm saying here is we're saying that, so the absolute value of the local error is less than or equal to some constant times h squared. And we're saying that kind of holds, you have a constant over the whole range of values that you're looking at, which mightn't necessarily be true. But here, it's actually what we're doing. So it's kind of like, to make this perfectly rigorous, and there's going to be a comment down the bottom, is actually quite difficult. I just want us to have a rough understanding of what's going on. When you add up loads of order h squared, you get an order h, for example. Reducing the step size by a factor of 4, we reduce the local error by a factor of 60. And if you understand that, that's fine. This thing that I'm writing now is an attempt to kind of explain this with maths as such. So the original error is kh squared. And so the new error is, we're going to say it's the same constant. And now it'll be h over 4 squared, because we're saying if we're quartering the step size. And if you do h over 4 squared, it'll be h squared over 16. So you get kh squared over 16. And kh squared is the original error. So you get the original error divided by 16. So that's why if you quarter the step size, the local error will be reduced by a factor of 16. Okay, what is the effect on the global error if we half the step size? Well, because, so what will happen is you half the global error. Again, we'll argue it in the same way. So the global error, and if you don't know what the global error is, you might have to look back at previous lectures, is order h. So we're going to assume that there's some global constant, that any global error is some constant. It'll be a different constant now. Like in particular, it'll be like tk star, where t is the width of the thing. But we'll just write k. H. Maybe we'll just write a dash there to signify maybe they're different errors here. Okay, so basically it says if you half the step size, you can see that the global error goes down by a factor of 2. Let's be a little bit more careful. So let epsilon 0 be the initial global error. I'll put a g on this just to be a bit more careful, because we don't want to get confused between local and global. Local is at each step, global is at the end over all the steps where you add up all the local errors. So this we're saying is some constant, which we'll call k dash times h. So the new error, global error, if you reduce if you halve the step size, will be that same constant times h over 2. And hopefully it's quite easy to see here. This is k dashed h over 2. K dashed of h is the original global error, so that's the original global error before you reduce the step size over 2. In other words, you have. Okay. Now I said there was a further remark. You mightn't have noticed, and I wonder if I possibly made the error. We might just go back. I'll pause and go back. Yeah, so I'm actually back on page 28 here. Now this analysis, and I won't explain why because I don't fully understand myself why, but this analysis does not hold if the derivative is in terms of x and y. So this analysis, just this analysis here, so if you want to fix this, it's a small, not that important point, but this argument is only if the derivative depends on x only. If you want to understand, it's kind of complicated. I don't fully understand it myself, but I'm quite happy to admit that to you. So basically what does that mean? When I did this in the exam question, I was a bit more careful. I didn't have the derivatives depending on x and y, just x. So there's a comment down here. If the derivative depends on x and y, this argument breaks down. If you want to learn how, you can go into this link here. It's about how previous local errors affect the estimate of the current local error. Basically, yeah, so the idea is that, so say with the, if it just depends on x, I think the local error only depends on x. But in fact, if the derivative depends on x and y, the local error depends on x and y. And what we're missing here is that the errors in the previous local errors, so we're getting errors in the y. So when we get to say the fifth step, we need to be a lot more careful because the errors can get bigger and bigger and bigger because the y's, we're actually far away on the y's as well. So we're saying, oh, the second derivative, whatever, depends on this y value, but the errors could have gotten so big. I know, I appreciate I'm kind of talking nonsense here. It's not a big story for us because, as it happens, the global error is still order h. What happens is the constant is a bit more complicated. I think we had like k star th. I think it ends up being something a bit more like k star e to the th, something like that. So it's a bit bigger than what we say, but it's still a multiple of h, and that's the important thing for us. So that's why we don't make a big deal and we don't go through the full analysis. Okay, so that's all of us on the Euler method.